Hey guys, today I want to talk with you about weak convergence in Banach spaces, or to be more precisely, I want to show you a small motivation how to derive the idea of the weak convergence. My name's Frank, and let's start with the definitions first. Well, as usual, we start with the strong convergence. I guess everybody of you knows this, but let X be a Banach space. So a Banach space is a complete normed space, and Xn be a sequence in this space. We now say that the sequence Xn converges strongly to some value x in the space big X. Well, if this limit here goes to 0 or is 0. In this case, we write Xn to x. Well, we can get very far with this definition, but at some point you may run into problems and you need a weaker definition, especially when it comes to infinite dimensional spaces. And as usual, the definition drops from the sky and we put the motivation afterwards. So let's start with the definition. Again, X is a Banach space, and now we need its dual space, X star. So the dual space is the space of all linear mappings from X to its underlying field, which is R. We're only dealing with field spaces here. Then we say that the sequence Xn converges weakly to its value x. Well, you can see the definition here. We take any linear mapping or any element from its dual space, so any linear mapping from x to r, then we calculate the values f of xn, and if this limit goes to f of x, and this holds for every linear mapping in f, every linear mapping or every element of the dual space, then we say that the sequence is weakly convergent. In this case, well, usually you write xn to x with this where the lower part of this arrow is missing. So how do we get from the first definition to the second definition? We start by considering finite dimensional spaces. So x should be now a finite dimensional space, so it more or less should be equivalent to the space Rn for some fixed n. Xn is again a sequence. Then we can show that the following statements are equivalent. Our sequence is strongly converging against x, and every component is converging to its associated component of x in R. The proof is quite straightforward actually. From 1 to 2, you just use the definition of convergence. I just marked it here in quotation marks as epsilon definition. Every student knows what I'm talking about. And then make use of the norm. Definition of the norm here. Of course, implicitly we use the fact that every norm in finite dimensional spaces are equivalent. And to get from 2 to 1, well, let's do a contradiction and assume that there is a component which is not converging to its associated component, and then just create a contradiction to the strong convergence. So this is straightforward. So how is this helpful in generating a motivation for the weak convergence? Well, take a closer look at point number 2 here. So every component converges to its associated component. And let's rewrite this a little bit. First of all, we introduce the mapping Vi. Vi basically takes the vector x, it maps it with ith component. And this is again a mapping from x to r. And now we call the definition of weak convergence. Well, in the weak convergence, there was the dual space involved. And the dual space, again, contained all linear mapping from x to r. And it's quite easy to see that Vi is in fact a linear mapping. So it is part of the dual space. So here now comes the dual space into our motivation. And we can extend the result from the slide before by adding a number 3. Xn converges strongly to x if and only if Vi applied to Xn is strongly converging to, I mean this is a convergence in R, if Vi Xn is converging to Vi. But this must hold for all I. This is just a reformulation of part number 2, right? There's nothing has happened here except that we introduced or that we constructed mapping so that we can introduce the dual space here. These functions vi, they are more. They are not only part of the dual space x star, they also form a basis of this dual space. Or to put it in other words, every linear mapping from the space Rn to R can be expressed as a linear combination of our functions vi. And this gives rise to a very interesting extension of our theorem. Because we now have the following equivalence: if xn converges strongly to x, if and only if v applied to xn converges to v applied to x, but this must hold true for all elements of the dual space, so for all linear mappings from Rn to R. The proof is quite simple, it's the same as before, just use the linearity and the basis property and you're done. But the interpretation is very interesting, because we can now pass information about our convergence of our sequence xn from the space X to its dual space and back. What do I mean with this? This is pass information from 1 to 3. This is somehow clear, but more interesting, we can go back from 3 to 1. So if we know what happens on all elements of the dual space, we know something about our sequence itself. Maybe this becomes more clear if you do a more quantitative approach. Think of a system which you can only measure the output through some measurements device. And our system is X, and our measurement device is an element of the dual space, because the output of V applied to our system is a number, a real number. This is something you can measure. And the measurement, of course, should be linear, because if you double the input, you want to double the output. So think of the dual space as measurements for our quantities X. And point number 3 says you can I put it here in nice words. If point number 3 is true, right? Well, then it means that a sequence converges as far as one can tell with any measurement device, because sometimes it is not possible to access our sequence xn directly, but you can use the measurement devices here. And the theorem says that, okay, if you know something about all measurement devices, then you know something about your system itself. And I think this is the best motivation I've ever seen in my whole life for the motivation of the weak convergence. I mean, I know all the funny facts about weak convergence and why you need this, but the physical interpretation is quite useful if you think about measuring a device and backtracking the output of your measurement devices and learning something about your system itself, because this is exactly what's happened here. You observe something, and from the observation you do you get some information about the system itself. Unfortunately, this only holds true for finite dimensional spaces. And the standard example, I just put it here, if you consider Rn, let n go to infinity, in quotation marks of course, then you get the space small l2. And if you construct a sequence by setting a 1 at the nth position, then you have a sequence which has nice properties, because for every component, we know that every component goes to 0 eventually if n is big enough. However, if you consider the norm, I put a norm here, this norm is always 1. So norm en minus 0 in this 2 norm is always 1. So we cannot have strong convergence against 0. But the sequence is weakly converging against 0. And I choose the specific example because you can see here that you still have the property that every component is converging to 0, and you have the weak convergence, so every observation in quotation mark is converging against 0, which is somehow the expected output. So now it's time for a small recap. We started with strong convergence, and from the strong convergence we moved on to the convergence of every component. which is point number 1 here, which somehow is weaker than strong convergence because, as this example shows, we have this property still available that every component is converging, but we lost the strong convergence. However, dealing with components is not always possible. It's possible here since we have something countable, but if you move on to Lebesgue spaces, this is not possible anymore. So we need something more, and we moved on, or we motivated the use of the dual space. And by using the dual space, we can measure something and extract some information about the sequence itself, if you want to put it in a more quantitative approach. And this weaker approach is very useful because if you go to infinite dimensional spaces, weird stuff happens and you lose something, but on the other hand, you gain something. Because if you think of, or maybe if you think a little further, why do we need this weak convergence and all this stuff? Well, because the formulation of the physical systems, for instance, if you're dealing with PDEs, for instance, well, they don't have strong solutions, but they have weak solutions. And these weak solutions are, of course, defined in the sense of weak convergence. So this is a very useful and a very powerful tool. And I guess many results of the functional analysis are not possible if you do not use the definition of the weak convergence. So that's all for now. I don't want to do the deep dive here right now. I just wanted to give a small motivation and what I think is helpful to understand the derivation of weak convergence. And one key is thinking of the dual space as measurement of a system. This is very helpful. And number 2, this is more mathematically correct. You can learn a lot about about some spaces by analyzing its dual spaces. I guess there's an X star missing, so this is of course X star. And a lot of things break when you go from finite dimensions to infinite dimensions. So take care and always stay interested in new stuff. Take care and see you in the next video.